What's up, guys? Today we're going to be talking about graph coloring and their connections to the Fibonacci and Lucas numbers and perhaps other sequences that we could find. Now, we are going to use something called 1-1 coloring, which basically means we can only color each vertex red or white. And the rule is that if two vertices are connected by an edge, both vertices cannot be colored red. So now let's go over two families of graphs. The first graph that I want to go over is the path graph, denoted by Pn. The path graph is simply a string of n vertices connected by n-1 edges in a straight line. For example, P1 is a single vertex, P2 are two vertices connected to each other, P3 are three vertices connected to each other, and so on. And the second graph I want to go over is the cycle graph, usually denoted by Cn. So the cycle graph basically forms a cycle of n vertices and n edges. For C1, that's simply a vertex connected by itself with a loop. For C2, that's two vertices connected in a loop. For C3, that's three vertices connected in a loop, also known as a triangle. In C4, the vertices are connected in a square, and so on. Okay, so let's try to apply our coloring system to the path graphs. For P1, there are two ways to color it, either white or red. For P2, there are three ways of coloring it. For P3, there are 5 ways of coloring. P4, there are 8 ways of coloring. So now you might realize that this sequence is starting to follow the Fibonacci sequence. So perhaps we could conjecture that Pn is equal to Pn minus 1 plus Pn minus 2. And we also see a similar thing with the ones below, but this time with the Lucas numbers. C1 is equal to 1 because it can only be white. C2 is equal to 3. C3 is equal to 4. And C4 is equal to 7. So once more, we do see a recursive relationship among the cyclic graphs. But this time, it's following the Lucas sequence, which starts with a 2 and a 1 instead of a 1 and a 1. So now the question is, how do we prove this? And to do that, I actually have some tools. The first thing I want to show you is the deletion tool. Say I had a path graph of size 3, so P3. Now I'm saying the number of ways to color P3 is equal to the number of ways to color the graph without an edge E. However, without this edge, we are overcounting the cases where these two adjacent vertices are the same color. So we have to eliminate the cases when they're red. We have to subtract the cases when these two vertices are red. And you can see when they are red, we know that the connected vertices to those two must be white. So over here, we actually have an empty graph, which is really just two path graphs of size 0, P0 times P0. All right, so we get this relationship. Furthermore, we could generalize for our graph G that the number of ways to color that would equal the graph G without the edge minus the graph G without the link of edge E. And the link of edge E is simply the subgraph that includes the edge, the vertices that are at the end of the edge, and the vertices connected to those vertices. So that's the link. In this case, the link of E is the whole graph, just by chance. So suppose that we have P4 once more. Now, I'm going to say the number of ways to color P4 depends on the number of ways which I can color it when vertex V is either red or white. Let's take the first case. What happens when vertex V is white? When vertex V is white, then we just remain with P3. How about the number of ways to color when V is red? Because V is red, all the vertices connected to V will be white. That leaves us with two vertices to work with. So the number of ways to color a path graph of size 4 is P3 plus P2. And we can generalize this for the relationship that Pn is equal to Pn minus 1 plus Pn minus 2. Because we know that P0 is equal to 1 and P1 is equal to 2, we have just proven that, in fact, Pn is equal to the nth plus 2th Fibonacci number. And if we look at what the coloring tool is really doing here, it's taking a graph G, you pick a vertex V, and then you delete vertex V from the graph. So it's the number of ways to color the graph without V plus the number of ways to color the graph without the link of V. And in this case, the link of a vertex is the subgraph of the vertex and all of its connected vertices. Okay, So now we have our two tools. Now we can move on to the Lucas sequence. So suppose I have a cyclograph of size 5. If we apply the coloring tool, you pick a vertex V, and the number of ways to color that without V is P4 plus the number of ways to color it without the link of V, so plus P2. Now, so this generalizes to Cn is equal to Pn minus 1 plus Pn minus 3. Now, suppose we had a cyclograph of length 5. If we use the edge deletion tool, then we have a path graph of size 5 minus a path graph of size 1. So we generalize this relationship by Cn is equal to Pn minus Pn minus 4. Okay, now we combine these two equations in a way that leads us to the recursive relationship for the Lucas numbers. Yeah, so the first thing I'm going to do is I'm going to shift the index of the first equation to Cn minus 1. And then I'm going to add the second equation in here. So I'm going to add these two equations together. So now I have that Cn plus Cn minus 1 is equal to Pn plus Pn minus 2. And of course, we know that from the first equation that this is simply equal to Cn plus 1. So Cn plus 1 is equal to the sum of the previous two cyclographs. So now we have our recursive relationship. With this, we can now prove that because C1 is equal to L1 and C2 is equal to L2, that Cn is equal to Ln. But you can see that from this relationship, if we convert this into Fibonacci and Lucas numbers, that the nth Lucas number is equal to the sum of the nth plus 1 Fibonacci number plus the nth minus 1 Fibonacci number. And from the second equation, if we convert it into Lucas and Fibonacci numbers, we find that the nth Lucas number is equal to the nth plus 2 Fibonacci number minus the nth minus 2 Fibonacci number. Let's have some fun proving more Fibonacci identities. For example, if I have a generalized path graph with R vertices on the left, 1 vertex in the middle, and S vertices on the right, then applying the coloring tool on this middle vertex V, I can say that the path graph of size R S plus 1 is equal to the path graph of size R times the path graph of size S plus the path graph of size R minus 1 times the path graph of size S minus 1. And now shifting the indexes over, we find that the rth plus S plus 1 Fibonacci number is equal to the rth plus 1 Fibonacci number times the S plus 1 Fibonacci number plus the rth Fibonacci number times the S Fibonacci number. And if we take a slightly different scenario, for example, if we had a path graph of size R plus S, but this time without the extra vertex, then this time applying the edge deletion tool to edge E in the middle, it will give us the number of colorings of PR times PS minus the number of colorings of PR minus 2 times PS minus 2. Okay. And, once again, shifting the indexes, we find that the rth plus S Fibonacci number is equal to the rth plus 1 Fibonacci number times the S plus 1 Fibonacci number minus the rth minus 1 Fibonacci number times the S minus 1 Fibonacci number. And the fun just doesn't stop here. You can prove so many identities about the Fibonacci numbers and the Lucas numbers and their relationship just purely through coloring graphs. Here I've listed out a few of my favorite identities. So I hope I taught you guys something really cool. So if you liked it, consider subscribing, and see you next time.